Welcome to this online colloquium of the Division of Mathematical Sciences at NTU. The talk will be around 40 minutes, and after this we have up to 20 minutes for Q&A. So we have quite a lot of time for questions, and you can send your questions already during the talk so that I can bring them up at the end then. So it would be nice if you can send your questions already in the chat. And our head of division, Professor Chan Song-Heng, will introduce the speaker. I now pass over to Song-Heng.
Good afternoon, everyone. I guess except for Professor Gowers, good morning. Welcome to the Division of Mathematical Sciences Colloquium, which is hosted on Zoom. I'm Chan Song-Heng, the head of Division of Mathematical Sciences. It's good to see many of our colleagues and students of NTU at this Zoom meeting. And to those of you from outside of NTU, Nanyang Technological University, a very warm welcome too. I'll just say a few words about the colloquium series and then I'll introduce Professor Gowers. So the COVID situation has brought about travel restrictions, and the division was not able to host any overseas visitors since March 2020. And then our division's colloquium series more or less came to a standstill as a result. So probably no one in my division remembers when was the last time we had a colloquium. The school was very supportive, and the division has decided to restart a series of online colloquiums with the aim of having one speaker every 2 to 4 weeks. We are deeply honored and grateful to have Professor Timothy Gowers to agree to be the first speaker of our colloquium series, giving us a great head start and setting the standard so high. Next, I'll just give a brief introduction of Professor Gowers. So Professor Gowers completed his PhD at Cambridge University under the supervision of Béla Bollobás. He was elected to be a research fellow at Trinity College and then a lecturer at University College London before returning to Cambridge in 1995, and was subsequently elected to the Rouse Ball Professorship at Cambridge in 1998. He is a winner of the Fields Medal in 1998 for his work in functional analysis and combinatorics. In 2012, he was knighted by the British monarch for services to mathematics. He is one of the most influential mathematicians today, and he has always been passionate about introducing mathematics to the world. In the interest of time, I apologize that I have only given a small selection of the awards and honors of Professor Gowers. So without further ado, let's welcome Professor Gowers to deliver the colloquium. The title of his talk is Szemerédi's Theorem and Additive Combinatorics.
Thank you very much for that introduction, and thank you very much for the invitation. It's very sort of flattering to be invited to give the inaugural colloquium in this series. I think really what I'm going to be doing in the next 40 minutes or so is just trying to present the area of additive combinatorics to you, just to give you a sort of snapshot of what that area is like. I'm not going to go into any detail about any mathematical arguments. I just want to leave you with an impression of what the field is like, which is a field I've been working in for, I suppose, about the last quarter of a century, which I really very much like and has all sorts of different facets to it. In fact, I should say before I even start that I will only be giving you a rather partial picture of the subject because it's quite a big area now, but it's an area that sort of developed over those last 25 years, although it has its roots in other areas, and I'll explain that a little bit. So without further ado, let me share my screen. Now, I hope that you can now see one slide.
Yes, it
there.
works. Yes,
good.
Works.
Okay, so I will start by talking about an area that additive combinatorics grew out of, and that's an area called combinatorial number theory, and I'll try to distinguish between additive combinatorics and combinatorial number theory at some point. The distinction is a little bit subtle and it doesn't matter too much, but roughly speaking, combinatorial number theory is looking at sets of integers and problems that you can formulate about those sets of integers. So the fact that you're talking about sets of integers makes it number theory, because you use the additive structure, maybe sometimes multiplicative structure of those integers. But the problems themselves, I mean, the fact that you're only looking at sets of integers rather than, let's say, more sort of structured sets of integers, or number fields and things like that, that makes it more combinatorics, and it gives it a very combinatorial flavor, because these sets can be completely arbitrary. We're not asking for them to have any particular structure. But instead of trying to define this in the abstract, I think it's better if I just give you an example of a really beautiful open problem in combinatorial number theory. It's called additive basis problem. And the idea is that an additive basis of the natural numbers is a set of positive integers with the property that every natural number can be written as a sum of two elements of that set of integers. So we call that an additive basis of order 2. If you start thinking about it, it's not completely easy to think of non-trivial examples of additive bases of order 2. But Erdős's question was, roughly speaking, how efficient an additive basis of order 2 can you find? So what he meant by efficiency there was that you'd like it to be the case that every single integer has at least one, or every single sufficiently large, doesn't make too much difference, but it's just convenient to say sufficiently large. So every sufficiently large positive integer can be written as a sum of two elements of A, but you don't want it to be writable in too many ways. So can you find an additive basis, i.e. every sufficiently large integer can be written as a sum of two elements of the set, but no positive integer can be written in more than, say, 100 ways? Or, which I think is probably what people think is the case, is it in fact the case that whenever you've got an additive basis, so whenever you can write every sufficiently large integer, there must be some that you can write in lots and lots of ways? An example to bear in mind here, which isn't an additive basis, but it sort of gives you the flavor of an additive basis, is the set of all squares. So it's not the case that every positive integer can be written as, or even every sufficiently large positive integer can be written as a sum of two squares. But you can write a pretty good fraction. There are asymptotics for how many positive integers up to n you can write as a sum of two squares, and it turns out to be, I think, about n over the square root of log n or something. Maybe it's n over log n, I've forgotten now. Which is getting close to n. So you might think maybe you could take the squares and do something with those, but nobody. Sorry about that. I think I just got muted by the host, but I've unmuted myself. I hope you can still hear me. Okay. Now I want to talk a little bit, just ever so slightly formally, about what you might say the object of study really is for an additive combinatorialist. So this looks all a bit abstract, what I've got on the screen here. I'm about to explain it. So I said we look at sets of integers, but mathematicians always like not just to think about the objects that they're looking at, but the maps that they care about between the objects. This is a sort of category theory way of looking at things. And in particular, when do we consider two objects to be essentially the same object? And in additive combinatorics, we consider two objects to be the same object if there's a particular sort of map between them. And the rough idea is that this map should preserve the additive structure of the two objects. So with that in mind, we define a function phi from a set A to a set B to be a Freiman homomorphism, or we'll just call it a homomorphism. And Freiman is one of the sort of founding fathers of the field. So they're named after him. It was his concept originally. But we'll call it a homomorphism if we have the following property, that whenever A1, A2, A3, and A4 are elements of A, such that A1 plus A2 equals A3 plus A4, then we also have that phi a1 plus phi a2 equals phi a3 plus phi a4. And so in other words, whenever you get two sums that are equal, then the sums of their images over in B have to be equal as well. That's what we call a homomorphism, or sort of additive homomorphism between the sets A and B. And I'll show you some examples just to give you an idea that actually additive homomorphisms can be somewhat interesting objects. Now, if you've got an additive homomorphism, that allows you to make sense of a function defined on sums of elements of A. So if I want to define psi evaluated A1 plus A2, an obvious thing to do would be, and I want to use phi somehow, an obvious thing to do would be to work out phi of A1 and phi of A2 and add them together. But there's a problem with that, which is that what if A1 plus A2 equaled A3 plus A4, and phi A1 plus phi A2 doesn't equal phi A3 plus phi A4? That would give us two different possible answers for psi. So in order to ensure that psi is well defined, we need precisely this condition here. We need it to be the case that whenever A1 plus A2 equals A3 plus A4, we also have that phi A1 plus phi A2 equals phi A3 plus phi A4. Once we've got that condition, this function psi is a well-defined function. It doesn't matter which pair of elements I chose, A1 and A2, that had the particular sum in question. And actually, we can also define another map on differences of elements of A, because this condition, if you just rearrange, it works out as A1 minus A3 equals A4 minus A2 implies phi A1 minus. So we can do this condition with pluses implies the same condition with minuses. So again, I'm speaking somewhat abstractly. Perhaps we can think about some concepts that are what I would call isomorphism invariant. So, actually, I haven't said what an isomorphism is. So I'll just quickly nip back to this slide. So an isomorphism is basically an invertible homomorphism for which the inverse is also a homomorphism. So if you've got a map from a homomorphism from A to B, and its inverse, it's got an inverse, and the inverse is also a homomorphism, then we call that an isomorphism. And that's when we call two sets essentially the same set. So the first thing I want to point out is that all arithmetic progressions of length k are isomorphic to each other. And or the concept of being an arithmetic progression of length k is something that is isomorphism invariant. That means that if I just take an arithmetic progression of length k and apply an isomorphism to it, I get another one. And I'm not going to prove that. Well, I mean, actually, what I'm giving here is a proof, but it's not. It may not be completely obvious that it's a proof, but that's not. I don't want to dwell on it too much. I just want to point out that if I want to define what it means for something to be an arithmetic progression of length k, one way I can do it is to say that there exists some d such that a2 equals a1 plus d, a3 equals a2 plus d, a4 equals a3 plus d, and so on. But it's not completely obvious if I do it that way that I've got something that's isomorphism invariant. But another way of saying what we have, what an arithmetic progression of length k is to say that each element of this sequence, I've written it as a set, but I really think of it as a sequence, is the average of the ones on each side. So A2 is the average of A1 and A3, A3 is the average of A2 and A4, and so on. Well, that guarantees that you step by the same amount as you go from each AI to each AI plus one. And that condition that each one is the average of the two neighbors, so to speak, can be written in this form: AI plus AI equals AI minus 1 plus AI plus 1. And that is exactly an additive relation of the form A1 plus A2 equals A3 plus A4. It just happens that A1 and A2 are the same element, but that's okay, that's allowed in the definition. And so because we've managed to define the notion of an arithmetic progression of length k just using equalities of this form, that shows that it's a concept that makes sense, so to speak, to an additive combinatorialist. We also, there's this condition here I've put in brackets, it's just to guarantee that A1 doesn't equal A2, because then all of them would be the same, and we don't want to consider, so to speak, a degenerate arithmetic progression where you step up by 0 each time as being a real arithmetic progression. But we can express that as well as saying A1 plus A2 doesn't equal A1 plus, or A1 plus A1 does not equal A1 plus A2. That guarantees that A1 doesn't equal A2. And here comes a second concept, which I'm introducing for two reasons. One is just to show that it's isomorphism invariant. But that's not the point I really want to emphasize. Really, I'd just like to say that some sets and different sets are of immense importance in additive combinatorics. So what is a sum set? If I take a set A, its sum set is defined to be the set of all sums of two things that you can make out of A. So it's a set of all possible sums A1 plus A2, with A1 and A2 belonging to A. And I haven't written the definition of the different set, but it's exactly what you would expect. A minus A is the set of little a1 minus little a2, such as a1 and a2 are in A. It's a set of all differences of two things. And here I just stress that you are allowed a1 to equal a2. So twice an element of A is also one of the elements of the sum set. And 0 belongs to the different set. What I said on the previous slide can be summarized as saying that if you've got a homomorphism from A to B, then it induces a map from A plus A to B plus B. That's just a way of saying what I said just now. If it's an isomorphism, then it's invertible, and the inverse is also an isomorphism, and that it's a simple exercise to show that that translates into this map being actually a bijection, because the inverse of the homomorphism will induce the inverse of this map psi. And so because you get a bijection between A plus A and B plus B, and in order to get it, we only ever used equations of the form A1 plus A2 equals A3 plus A4. That shows that the size of the sum set and the size of the different set depend only on A up to isomorphism. If I take an isomorphic set, its sum set will be the same size as that of the set A. So sizes of sum sets are something that we are very interested in additive combinatorics. And not just because it's something we can define, as I'll try to explain later on. It's something that kind of comes up in nature, let's say. Now, the next thing I think it's important to say is that I've just talked about sets of integers, but mathematicians are sort of compulsive generalizers, and additive combinatorialists are no exception to that. And it got gradually realized that a lot of the things that people were saying about sets of integers can either be generalized directly into more general contexts, or perhaps even more interestingly, can be generalized with some difficulty to further concepts. So why do I say that's more interesting? It's because if there's a sort of suggested generalization, but it's difficult to carry out, then you've got some interesting maths to do, and we're always on the lookout for interesting things to do. So, for example, we like to look at subsets not just of the integers, but also a two-dimensional grid of integers. And of course, why stop at 2? We could go for a d-dimensional grid of integers. Later on, we'll see that that's a convenient thing to do. But once we've got that far, we say, well, those two sets, z squared and z to the d, are abelian groups. Why not look at other abelian groups, like cyclic groups? And again, those are things that come up very naturally. It's in many contexts. If you're looking at a problem about integers, you find that you want to think about cyclic groups. And once you started thinking about cyclic groups, well, what about products of cyclic groups? And you end up rapidly talking about abelian groups in general. And for example, all the definitions I just gave for a Freiman homomorphism and a Freiman isomorphism generalize with no difficulty at all, in fact, essentially word for word, to subsets of abelian groups. And I think the next generalization is going to be rather unsurprising. Once you've talked about abelian groups, what about groups? There, it's not quite so straightforward to define things, but when you sit down and think about it a bit, a natural definition of a Freiman homomorphism comes to mind. But it's just because you can't swap things around, it's the little extra phenomena come in. But what I really want to say here again is not how you do it, but just to say that after several years in which additive combinatorialists were really concentrating on subsets of abelian groups, they not only, so this was not a generalization for the sake of it, they not only started thinking about subsets of groups in general, but they found that that was extremely fruitful and fed into group theory, geometric group theory. All of those things have recently, or fairly recently, benefited from ideas from additive combinatorics. Okay, I want to talk about another concept which is also of interest to additive combinatorialists, and that's something called a multi-dimensional arithmetic progression, which turns out also to be an isomorphism invariant. So in other words, a concept that makes sense up to isomorphism. And I just want to illustrate an isomorphism here. So just concentrate for the moment on the top bunch of numbers. So those are the numbers 7, 10, 12, 13, 15, 16, 17, 18, 21, 22. And I've written them in a grid like this, because if I write it in a grid like this, you can see very much more easily the structure of the set of integers that I've chosen. So if you go along any row, you're adding 5 as you go along. And if you go down a column, you're adding 3 each time. So we call this a multi-dimensional arithmetic progression because it's a little bit like an arithmetic progression where you add the same thing as you go along. But now instead of just having one direction, we have 2 directions. So every time we go along in this direction, we add 5. And every time we go down in this direction, we add 3. So those are the 2 dimensions. In one dimension, you add 5, and in the other dimension, you add 3. Now, if I look here, if I think of these points as belonging to z squared, we find that we have a grid of 20 points, a 5 by 4 grid. The points 1, 1, 1, 2, 1, 3, and so on. And if I just map in the way that's suggested, so in other words, 7 goes to the point 1, 1, 12 goes to the point 1, 2, 17 to the point 1, 3, and so on. Actually, it might have been more natural, since I've drawn these going horizontally, to go 1, 1, 2, 1, 3, 1. I apologize for that. So I've got a slightly strange isomorphism, but it's a perfectly valid one. But anyway, I do this map, so 28 here maps to the point 3, 4. Then it's not difficult to check that that really is an isomorphism. In fact, let me just do one small calculation just to convince you. So, for example, 7 plus 31 is 38, and 15 plus 23 is 38. If I look at 1, 1 plus 4, 4, I get 5, 5, and 2, 2 plus 3, 3 is 5, 5. I'll do one more. 15 plus 36 is 30 plus 21. They both equal 51. And similarly here, 2, 2 plus 4, 5 equals 2, 5 plus 4, 2. And these are not coincidences. That's very easy to prove that this is an isomorphism. So another way of justifying the terminology that this is a 2-dimensional arithmetic progression is that it's an isomorphic image of a little 2-dimensional grid, just in the same way as a normal arithmetic progression is an isomorphic image of a 1-dimensional grid. And I'll come back to, I'm talking about various things, and at some point soon I will tell you a bit more about why I'm interested in all these concepts. But now let's go to the other part of my title, Szemerédi's theorem. And what I've got here on the screen is a bunch of fairly arbitrary numbers. Actually, it's more than arbitrary. I literally chose this sequence of numbers by Googling random set of integers, finding a website that allowed me to choose a subset of integers within a given range with a given probability of occurring. And so I chose a range 1 to 300, and my probability was 1 in 5. So this was a random set of a fifth of the integers from 1 to 300. But I want to stress actually that I chose these ones randomly, but Szemerédi's theorem actually concerns not random sets, but just any old set. So I could have chosen it completely non-randomly if I wanted, and the theorem would apply. I haven't told you what the theorem is, but we'll come to that in a minute. I just want to show you the theorem, so to speak, in action, and then I'll tell you what it actually says. So what we're looking for here with Szemerédi's theorem is arithmetic progressions. So we're looking for, here's one, 35, 36, 37. That's a very simple example of an arithmetic progression. And a slightly less simple 37, 40, 43. And in fact, I've worked on this a little bit in advance. And let's have a look at quite a few other ones. So I've used colors just to sort of pick out some of them. So we have 10, 40, 70, 123, 126, 129, 271, 272, 273. Then we have this rather more interesting one, 33, 133, 233. And another one I was quite pleased to find, 112, 141, 170, which has where you're adding set 29 each time. And there are others. There's certainly not an exhaustive list, but it's just a few. And if we look a teeny bit harder, we find that there are actually some arithmetic progressions of length 4. So 82, 92, 102, 112. That's jumping up by 10 each time, or you could start at 216 and add 17 each time. I looked quite hard for more arithmetic progressions of length 4. I can't be absolutely sure there aren't any, but I didn't find any more, and I think there probably aren't any of length 5. So with those examples in mind, there are some questions that one can start to ask, like under what circumstances can we say that a set of positive integers must contain an arithmetic progression of at least some given length? And Szemerédi's theorem gives a rather wonderful answer to that question. I've written it in a formal way, and I'll say what it says more informally in just a moment. But the formal thing is for every delta, so that's going to represent a density, and every k, that's going to be the length of arithmetic progression that we're looking for. You can find an n. Basically, that means if n is sufficiently large, such that every set of integers between 1 and n, where you choose at least delta n of them, must contain an arithmetic progression of length k. So if I wanted to summarize that in a sort of slogan, I would say dense sets of integers contain long arithmetic progressions. But if you want to be clear what you mean by that statement, you have to start thinking about quantifiers. For every delta and every k, there exists an n such that every, for all there exists for all. In other words, or we can think of it in another way, you get to choose delta and k. So you want to make it difficult for me. So you might say, well, delta will be 1 over a million and k will be 10 billion billion or something like that. Then I have to give you an n. And I try to make my n fabulously large to make life difficult for you. At that point, your challenge is to find a set A of integers between 1 and n, my fabulously large n, but you only have to choose 1 in a million of them on average. And you've got to avoid there being an arithmetic progression of length 10 billion billion. And Szemerédi's theorem tells you, remarkably, I'm going to win that game. Even if you choose an incredibly small density and an incredibly large k, I can make n sufficiently large so that whatever set you choose from 1 to n of that density, you will not be able to avoid an arithmetic progression of that length. So this theorem has a long history, and this is by no means all the history of the theorem. So it started out life as a conjecture due to Paul Erdős and Paul Turan. And it remained open for a long time. And the first significant progress towards the conjecture was by Klaus Roth in 1953, who proved that whatever the density is, if n is large enough, you can find an arithmetic progression of length 3. So not for any old k, but at least the density can be very, very small. And his proof used Fourier analysis in a rather beautiful way. For various reasons, that Fourier analytic proof didn't straightforwardly generalize to longer arithmetic progressions, and so the problem remained open for quite a lot longer. And then Szemerédi, actually he found another proof that was more purely combinatorial, even in the case when k equals 3, which then allowed him, it gave him an argument that he was able to generalize. But even that was a very difficult process. So by 1969, he'd got to progressions of length 4, and then it took another, these are actually dates where the papers were published rather than, well, I don't know precisely when he actually proved them. And then he got the general case. The paper came out in 1975, and it's a rather extraordinary, long paper with a very complicated dependence of the various lemmas. There's a rather amazing diagram near the beginning of the paper that shows how the lemmas depend on each other. A couple of years later, a very influential paper was published by Hillel Furstenberg, who showed that you could prove Szemerédi's theorem using an ergodic theory approach. And when I say using ergodic theory, I don't mean he just looked at ergodic theory and took some tools off the shelf. He had to develop tools in ergodic theory, which he did. And that turned out to be a much more fruitful proof from the point of view of generalizing. So there were several extensions of Szemerédi's theorem, like a multi-dimensional version of the theorem and various other things that, at least initially, were proved using ergodic theory, and nobody could see how to do them using any other approach. And so I've missed out a lot of things. There was progress on quantitative progress for progressions of length 3, but I'm not going to talk about that. I just want to talk just about the theorem itself. So in 2001, and again, this is where the paper came out, the actual proof I obtained a couple of years earlier. I managed to show that you could, in fact, generalize Roth's argument in a non-obvious way. So it was possible to use Fourier analysis for progressions of length 4 and above, but not in quite the way that one might expect. And it did involve some combinatorial arguments as well. And then there had been actually already by that stage a suggestion by Rödel, Schacht, and Skokan for an approach using hypergraphs that might be able to, or if you could do such and such a, if you could prove such and such a result, it would enable you to use hypergraphs to prove Szemerédi's theorem. I don't want to talk too much about hypergraphs, but roughly speaking, a graph is a collection of points with edges. So each edge is just a pair of points. And a 3 uniform hypergraph, instead of looking at pairs of points, you look at triples of points. And a k uniform hypergraph, you look at k tuples of points. So there are sort of higher dimensional generalization of graphs. And I should say that so this program of proving Szemerédi's theorem was eventually carried out. And again, it was 2004 was not exactly when it happened, but it's when the paper of Nagel, Rödel, and Schacht came out. Mine got sort of sat around for a while with a journal and came out in 2007 actually, but the proofs came out at the same time. And then a rather interesting further development was that there's a generalization of Szemerédi's theorem called the density-Hales-Jewett theorem. And that had been proved using ergodic theory techniques. But in 2012, a big online open collaboration that I initiated, well, again, this is the date of the paper, actually, this happened in 2009, came up with a combinatorial proof of the density-Hales-Jewett theorem, which then implied Szemerédi's theorem by, I think, a somewhat simpler proof than some of the earlier proofs. So that was also very sort of something we were all quite pleased about. So the thing I think that you'll be quite struck by, and I want to stress here, is that one theorem, you might think, this is very strange, you've got one theorem, it's got 5 proofs, and surely they're all fairly similar in the end, but actually they're all really quite interestingly different. Each one of these proofs, the 75 proof, the 77 proofs, the 2001 proof, the 2004 proof, and the 2012 proof, they are each really noticeably different. They do have something in common, and that I'm going to talk about in a moment. But I think this is sort of indication that it is a remarkable theorem. And it's, in some ways, you could think of it as the central theorem additive combinatorics. So I said in my, I think I said in my description or my abstract of the talk that somehow Szemerédi's theorem leads on to some other interesting results in additive combinatorics. And that's very much the case. Oh, I see I'm getting a little bit short of time, but let me, so in the proof, my Fourier analytic proof of Szemerédi's theorem, which I'm not going to say anything about, I'm just going to say that there arose in the proof, in a natural way, or there arose while I was thinking about the proof, a dense subset of Zn, that's my notation for the cyclic group of order n. So we had a dense set, that means a set of at least 1% of the elements or something, and a function from that set to Zn, which had the property, not that, it wasn't a Freiman homomorphism, so it wasn't the case that whenever a plus b equals c plus d, phi a plus phi b equals phi c plus phi d, but it was the case that that happens a lot of the time. So for 1% of the times when a plus b equals c plus d, you get that phi a plus phi b equals phi c plus phi d. So that condition came out, and I wanted to know, can you now say anything interesting about the function phi, given this information that it's additive much of the time? It's not additive all the time, but it's additive a lot of the time. What sort of functions can have this partial additivity property? Now, if you look at the graph of the function phi, we call it gamma, then that graph has a lot of quadruples, a, b, c, d, such that a plus b equals c plus d. So the a here is now the pair a comma phi a from up here. So a is now an element of the graph of the function. So I've sort of changed notation. So if you've got a set, when I say a set, I mean a subset of some abelian group. In this case, it's the abelian group Zn squared. That contains a lot of, so to speak, little bits of additive structure, little bits of solutions to this equation. Does that mean that the whole set must have some sort of additive structure that somehow explains this phenomenon? And so I've just repeated the question up here. And we can make a simple observation. Supposing the set had a small subset. So remember, gamma is a set of size n. Supposing we knew that gamma plus gamma had size at most 100 times n, c is just some old constant, so I've chosen 100, then necessarily, because you've got approaching n squared different possible ways of adding two elements of gamma together, if there are only cn possible sums, then many of those sums have to be the same as each other. And you can use that to show that, in fact, there must be at least n cubed over big C of these quadruples, where you get this, satisfy this equation. So we have that observation, and then there's a theorem called the Szemerédi theorem, which says that actually something a bit like a converse of that is true as well, which is that if you've got lots of quadruples like this, then your set must in fact have a large subset with a small subset. So it's not necessary that the whole set has a small subset, but it must have a large subset, at least. So we could say something like at least 1% of the elements of gamma form a set with the property that its subset is at most some constant times the size of it. So to say it in a sort of, again, in a slogan, sets with lots of additive quadruples have large subsets with small subsets. So that's not a totally easy theorem to prove, but it then moves the question on to the following question. If you've got a set of n integers with a small subset, what can you say about that? And this is a question that has a remarkably more precise answer than you might think. But in order to say what that answer is, let's first just think a little bit about some examples of sets that have subsets that are not very large. So one example is arithmetic progressions. If A is an arithmetic progression of length n, say, just for the sake of example, a set of numbers from 1 to n, just for simplicity, but because of this invariance, it doesn't actually make any difference what arithmetic progression I choose, then a plus a will be the set of numbers from 2 up to 2n, that's 2n minus 1 of them. So we get that the subset is at most 2n. We can take c equals 2 in the case of arithmetic progressions. If we take, say, a two-dimensional arithmetic progression, then you sort of expand by 2 in both dimensions, and that means you can take c equals 4. And if you take a d-dimensional arithmetic progression, then you can take c equals 2 to the d. So multi-dimensional arithmetic progressions, as long as the dimension isn't absolutely huge, give you examples of sets where the sum set is not too large. And another little observation to make is that if you've got a set with a small sum set, say I've got my A such that the sum set A plus A has size at most a constant times n. And if I take a large subset B of A, then the size of B plus B is still at most C times n, because the sum set is a subset of this sum set. But B has size pretty close to n, and therefore the size of B plus B is not very large compared with the size of B. You get a constant C. It's a bit larger than the constant that you had for A, but as long as B is a fairly large subset of A, it's not too much larger. So large subsets of multidimensional arithmetic progressions we've got to so far. And then Freiman's theorem says, you write down just a handful of examples that you can think of. It turns out you can't do any more. So I've written Freiman's theorem very informally. What it says more formally is that if A is a set of n integers such that the sum set has size at most a constant times n, then there must be a multidimensional arithmetic progression where the dimension isn't too large, such that A is a large subset of that multidimensional arithmetic progression. So we get some sort of structural object, a multidimensional arithmetic progression, that completely explains why A has a small sum set. Let me just check the time. So I really should be stopping. I left myself with various slides that I don't have to present, but I do want just to do this last slide because it's really a very important theme in additive combinatorics. It's the interplay between structure and randomness. So I've just talked a little bit about structure. So something I also briefly mentioned earlier, that I had a random set. It turns out that for Szemerédi's theorem, if you take a random set, it's rather easy to prove that it's got long arithmetic progressions, because it just has the number of arithmetic progressions that you would expect of a random set, and that's something that you can calculate very easily. So if you want to try and find a counterexample to Szemerédi's theorem, or a good bound, then random sets is actually not the way to go. Now, that, it turns out, it can be extended from random to what we call quasi-random sets. So quasi-random set is something that sort of looks like a random set, but doesn't actually have to have been generated randomly. And this is something that you might, that sounds a little bit vague, but it turns out that it can be made precise. And more interestingly, it can be made precise in various different ways. And some of the ways in which it can be made precise work for some purposes and some work for other purposes. And that's actually a very important aspect of various proofs of Szemerédi's theorem. So we can deal with random sets and we can deal with quasi-random sets. And then the final sort of piece of the puzzle is that if you have a set that's not quasi-random, and this is typically the hard part of the argument, then you can identify just a tiny little bit of structure. So in the case of Szemerédi's theorem, if you've got a set that's not quasi-random, so you can't deal with it easily, then after a long argument, you find that you can find some little portion of the set that sits inside an arithmetic progression where the density is bigger than the density of the original set. And that allows you to iterate. You sort of go from the original set, either you're done or you find a part where it's a bit denser. Then either you're done or you find a part that's a bit denser again, and the density sort of keeps going up and up until eventually it hits 1 and you have a contradiction. And Szemerédi's theorem is proved. I'm hiding a vast number of details there, but anyway. But this contrast between the random looking sets and the more structured looking sets, every single known proof of Szemerédi's theorem is based in some way, not always very explicitly, but in some way on this sort of dichotomy between randomness and structure. So I think, given the time, I think that's a rather good place to stop. There's all sorts of nice other things that I could tell you, but there's I mean, maybe some of them come up in questions, I can mention them, but for now I'll stop.
Yeah, thank you very much for your talk. There have been no questions in the chat, so if anybody has a question, please just unmute yourself and ask your question. Any questions?
So a
Hello.
question from here. Actually, I saw you have just mentioned the last one about the Szemerédi theorem about using this density version of the Hales-Jewett, right?
Yes.
Yeah, but the Hales-Jewett is actually a multi-dimension version of the van der Waalen. And this Szemerédi theorem is actually density version of the van der Waalen, right?
That's exactly right. Yes.
So then you say, okay, I get this kind of the hints like Hales-Jewett imply, it's actually generalization of this. What is that? The van der Waalen. And then how about the density version? You get this density version of the Hales-Jewett, and it implies this Szemerédi theorem. Anything like this kind of the misunderstanding from my side, like, okay, because I see, okay, you have A, and then you put A implies B, and then A plus implies B plus, and now you say, okay, this is actually used as, in some sense, looks like a strong version to imply this, weak version.
So it is the case, I'm not sure whether I'm going to answer your question, but it is the case that we've got something that we like in maths, a sort of rectangle. We've got A is to B as C is to D. So A is van der Waals theorem. Sort of, B is Hales-Jewett. C is density van der Waals, in other words, Szemerédi theorem, and D is density Hales-Jewett. And it's also the case that the way that you can deduce van der Waals theorem from the Hales-Jewett theorem is essentially the same as the way that you can deduce Szemerédi's theorem from the density Hales-Jewett theorem.
Oh, okay. I saw this. Okay. Yeah. So
basically,
like a density version implies density version. That is, I think, when I saw that one, I thought that is okay. You have these two versions, and then density version looks like implies again. Looks like this is wrong point. Yeah.
I mean, I can sort of basically tell you how you do it. So supposing you've got, let's look at progressions of length 3. So then the density Hales-Jewett theorem is about subsets of 0, 1, 2 to the n. And if you think of each sequence 0, 1, 2 in 0, 1, 2 to the n as being the ternary representation of a positive integer, then you take a dense set of positive integers up to 3 to the n. You pull it back to 0, 1, 2 to the n, apply the density Hales-Jewett theorem, that gives you a combinatorial line of length 3. Then you map it back to your set of integers, and you just have to check that the image of this combinatorial line is an arithmetic progression of length 3.
Okay, I think, I understand that,
But it's not just any old arithmetic progression, it's a very special arithmetic progression of length 3. So you're actually proving a much stronger theorem when you prove the density Hales-Jewett theorem.
Yeah. Okay, thank you.
Are there any other questions? Any questions?
Hi, I have a question.
Hello.
So in graph theory, especially like in probability also, there is a Szemerédi's regularity lemma, which is used to study dense graphs. And I guess there's some sort of connection between this and the Szemerédi's theorem. Could you say a little bit more about the connection?
Sorry, you said in graph theory?
The Szemerédi's regularity lemma.
Okay, so one very important connection is that, as you may well know, but not everybody will know, that there's this result Szemerédi's regularity lemma, which is an absolutely essential tool in graph theory, but it originally came into existence because Szemerédi himself realized that he needed something like that, or that something like that would be useful to him in order to prove Szemerédi's theorem. So the original motivation for Szemerédi's regularity lemma was in order to prove Szemerédi's theorem. The next thing to say is that there's been a very important interplay between the regularity lemma and Szemerédi's theorem. So something I didn't say about the hypergraph approach is that the way it arose was that Imre Rouge and Szemerédi came up with a beautiful proof of Szemerédi's theorem, a new proof, for progressions of length 3. that used the regularity lemma for graphs. So they managed to convert it into a graph theory problem, or maybe not exactly convert it, didn't translate it, but they managed to show that it followed from a statement in graph theory, which they identified. So it was an achievement just to think of the right statement in graph theory that could be used. They did that. And the statement in graph theory could be proved using, it's a statement called the triangle removal lemma. In fact, let me just quickly say what it says. It says, because this is also a result that's of huge interest to all additive combinatorialists, it says if you've got a graph with few triangles, then you can remove a small number of edges from that graph in order to obtain a graph with no triangles. I've stated it in qualitative language, but you can make it a precise statement. Part of the reason that's an interesting statement to additive combinatorialists is that we still don't know even approximately what the right bounds are in this lemma. But anyway, Szemerédi's theorem for progressions of length 3 follows by an easy but clever argument. And then the idea of the hypergraph approach, it then became noticed that, so it's natural to think, how do you generalize this graph theory argument in order to prove the result for longer progressions? And the right answer turns out to be, you turn to hypergraphs. You try to generalize the graph theory result to hypergraphs. So you want to come up with a suitable hypergraph regularity lemma. But for various reasons that I can't go into right now, that turned out to be much, the generalization was absolutely not a straightforward one, and the hypergraph regularity, and also something called a counting lemma that goes with it, those lemmas are considerably more difficult than the graph theory versions. And then one final thing, what does the regularity lemma say? Roughly speaking, again, this is for people who've not seen it, roughly speaking, it says, given any dense graph, you can partition the vertices into a small number of sets, such that between almost any pair of those sets, the graph that joins those two sets looks like a random graph. It's a quasi-random graph in a certain sense. So to say that in the form of a slogan, every dense graph is made out of a small number of quasi-random pieces. So that's just, I'm mentioning that because I said that in every single known proof of Szemerédi's theorem, we have this notions of quasi-randomness and structure coming up. And in the hypergraph approach, they come up because we're using this regularity lemma, which is all about splitting things up into quasi-random pieces.
So there has been one question in the chat. Arithmetic progressions are linear sequences, xn equals d times n plus c. What if the arithmetic progressions are replaced by quadratic expressions, by quadratic sequences?
Well, that's a great question, and it's been answered. So there is an incredible generalization of Szemerédi's theorem called the polynomial Szemerédi's theorem, and that says, well, I'll give you first a special case, and then I'll try to describe the general results. So the special case is, supposing you wanted to find an arithmetic progression where the common difference was a square each time. So you want to find, you know, something like, well, I had an example actually, 33, 133, 233. So the common difference there was 100, which is a perfect square. So could you add the extra condition to Szemerédi's theorem that you want to get a perfect square? And the answer is actually, yes, you can. And something much more general is the case that if I have polynomials with integer coefficients p1 up to pk, and you have the extra condition, because otherwise there are easy counterexamples, so you have to add the extra condition that each polynomial vanishes at 0. So for example, well, and then you're looking for a plus p1 of d, a plus p2 of d, all the way up to a plus pk of d. So if those polynomials p1 up to pk are just x, 2x, 3x, and so on up to kx, then you get back to an arithmetic progression. But it's also the you're looking for those. The polynomial Szemerédi theorem tells you you can find them if n is large enough and you've got a positive density. So for example, you can find, supposing you wanted to find a plus d squared, and a plus 2d cubed or something, you could do that, or a plus d squared and a plus d cubed plus d to the fourth. Those sorts of things can all be done. That was first proved using ergodic theory techniques. And now that's actually a case where the general result is, I think, still only known using ergodic theory techniques, but special cases of it with much better bounds or with quantitative versions have now been obtained. So the world expert, well, maybe two world experts are Sarah Palouse and my mind's gone a bit blank suddenly, Sean Prenderville. But there are various other people working on such problems as well. So it's still a thriving area of research to come up with a finitary, more sort of analytic proof of this theorem. There are various reasons that the proof of Szemerédi's theorem itself is quite hard to generalize, or at least some of the proofs of Szemerédi's theorem are hard to generalize.
So we are almost out of time, but we would have time for one more question. Any question? Any further question? So there is one question in the chat. We know that the converse of Szemerédi's theorem is not true by the Green Tau theorem. My question is that how close is the condition of positive density to equivalence in Szemerédi's theorem? And also, what is the role of primes in additive combinatorics?
Yeah, so let me just, my next slide would have answered that question, so I might as well just put it up. I won't talk you through it, but I just feel it's wrong not to put it there. So the question is not exactly talking about, it's slightly complicated to say what a converse to Szemerédi's theorem would be, but I suppose one could argue, one can certainly ask the question, and this is a question that's still pretty open. How dense does a set need to be in order to guarantee that it's got an arithmetic progression of length k? And we do not know whether a set with the same density as the set of primes must contain an arithmetic progression of length k. So the Green Tau theorem, which shows that the primes contain arbitrarily long arithmetic progressions, does prove what it says, but it doesn't just use the density of the primes, it also uses facts about the way the primes are arranged. I've given a very, very rough sketch of the proof down there. Let me just, so steps 2, well, particularly step 2 is something where they very much needed properties of the primes in order to do it. So I hope you've had time just to have a sort of quick read of that. And then just, I'll go to the following slide. So this is a famous question of Erdős, which is very closely related to the question of how dense does a set need to be in order to guarantee that you've got progressions of length, of arbitrary length. So if you've got a set of integers that's sufficiently dense that when you take the sum of the reciprocals of the elements of that set, it tends to infinity, or it equals infinity, must that contain arbitrarily long arithmetic progressions? And here's a condition that the primes do satisfy, but we don't know whether all sets that satisfy that condition must contain arbitrarily long arithmetic progressions. I would say that's the most famous Erdős problem that's still open. Perhaps even famous, even amongst the ones that have been solved. So a very recent piece of progress within the last year is that the answer is yes. Well, not for arbitrarily long, but it's yes, it's true for progressions of length 3. So this density is sufficient to guarantee progressions of length 3. And the rough state of the art is that if you've got density, so the integers from 1 up to n, if you've got density roughly 1 over log n, but just a little bit better than log n now, that gives you a progression of length 3. And my proof for longer progressions requires density, something like a power of 1 over log n. So quite a long way more dense than the density of the primes. And best lower bounds are quite a lot less dense than that. So there's an enormous gap between the density of the densest sets that we know of that do not contain arithmetic progressions and the density for which we can prove that there must be arithmetic progressions. It's still, so from the quantitative point of view, Szemerédi's theorem is still a pretty wide open problem and a very, very interesting one, and seemingly an extremely hard one. But maybe somebody will come along someday with a brand new idea that will make it easier. But I think just to sort of push the existing techniques, which I think is roughly what Bloom and Sisask did for length 3, and their paper was something like 75 pages, just to give you an idea. Not a simple proof at all.
Okay, and I think we need to stop at this point. So I would like to thank Professor Gowers again for his very interesting talk and for answering the questions, and also thanks to all for joining at this inaugural colloquium talk. And thanks for joining, and let's stop for today.